Hello there, welcome to our third flipped learning session today we're going to be looking at Young's modulus and this idea of stress and strain. But first, hopefully you'll recall that in the previous lesson, in lesson 2, we looked at testing materials and you drew a stress-strain graph for a material, for a wire. So what I'd like you to do is, on that graph, can you draw for me the areas, make sure you've got drawn on there, the areas of plastic and elastic deformation. If you can't quite remember what plastic and elastic deformation is, refer back to our second flip, because that's where we covered those definitions. But on your graphs from the lesson, can you just quickly add that in, shade in the areas of plastic and elastic deformation. Okay, so you probably had a force extension graph that looked probably pretty similar to this. Okay, a straight line region and then some sort of curve and maybe something that looked like that. Okay, so if we were to add on our areas of elastic deformation, we could say that this area here is where all of that where that all takes place. So then that leaves us with this part of the graph here. Okay, which is where all the plastic deformation is. So this is all plastically deforming, and then this section here is the material deforming elastically. Elastic deformation. Okay. Just quickly add that in. So elastically deforming. Okay. Okay, this point here is known as the elastic limit. So make sure you've got that onto your graph as well. Okay, hopefully you've got all of those key ideas onto your graph. We're going to come back to this idea of force extension graphs, this kind of shape as well, in our next lesson, in our third lesson. So make sure you've got those ideas in your head and that understanding that the elastic deformation happens in this linear region and the plastic deformations happens in this non-linear region, and the transition point between the two is known as the elastic limit. Okay, so the first of our new key terms that we talked about today was strain. So let's introduce this idea of what is strain. Okay, well, strain is equal to X over L, where X is extension and L is original length. Okay, now I think I've got that written on your sheet, but there's a few gaps, so make sure you've got the gaps filled in. And then also, whilst you're doing that, can you have a think about what is the units for this quantity strain? Have a look at the things that are going in, the two quantities going in, see if you can come up with what the units are going to be. Pause the video and have a go. Okay, so what you should find, okay, once you've filled in the gaps and had a think about the units, is that actually strain is a dimensionless. So what you should find is that strain is actually a dimensionless property, okay, of a unit. We've got extension going in, which is measured in meters, it's a distance, and we're dividing it by length, which again is a distance, it's measured in meters. So if we were to have that written, we would be having meters divided by meters, and of course they would just cancel out. So we're effectively left with a unitless or a dimensionless property. So make sure you've got that added onto your sheet. Make sure you specifically write down that strain is a unitless property. Okay, and then once you've done that, we'll move on. Okay, so what I've got on the board here are 4 new keywords for you: tension, compression, shear and torsion. They're probably all words, or certainly the first 2, maybe 3 in there, that you might come across in everyday English language. But what I would like you to do is, using books, the internet, however you like, can you write down on your sheet a definition for each one of these, a scientific physical definition, not necessarily the English definition, although of course the two are related. So pause the video, have a look at various different sources and see if you can write down some definitions for those. Okay, once you've done that, once you've got those definitions down, I'd like to have a look at these 2 bars. Okay, we've defined strain already, and hopefully now you've got definitions for tension and a definition for compression. So what I'd like to do is add on some force arrows to show this bar undergoing a tensile strain and this bar here undergoing a compressive strain. So have a think about your definitions for both strain and tension and compression, and see if you can add on 2 force arrows to show these 2 bars under tension and under compression. Pause the video, have a go. Okay, so what you should have drawn on is that this bar here under tension will have 2 force arrows operating in opposite directions, okay? That is what tension is. Tension is a pulling force, okay? Tension tries to pull things apart, okay? So that's hopefully what you've got for here, and then compression is the opposite of that. You'll find a compressive force pushes, okay? So the force arrows are acting in the same direction, okay? If you haven't got those, didn't quite get them right, correct them, change them out, add them on. Okay, so hopefully you've all got those drawn in. So let's move on. Let's have a think about this problem here. I've got a metal bar, okay, with a force being applied at one end, and you can see that it's being bent, okay? The bar is undergoing a shearing force, a shearing motion. So what I'd like you to do, what I'd like you to think about is what parts of the bar are undergoing tension and what parts of the bar are undergoing compression. So what I'd like you to do is, can you just quickly sketch this onto your sheet and then label the areas that are undergoing tension and the areas that are undergoing compression. Pause the video, have a go. Okay, hopefully you've had a go at that, and hopefully you can see that this part of the bar at the top, okay, this top part of the bar will be undergoing a tension force, okay, okay, and similarly, or this part of the bar will be undergoing compression. Okay, hopefully you can see that, and hopefully that makes sense to you. I mean, at the end of the day, sort of the top bit of the bar is being almost elongated, it's being stretched, okay, because it's having to go further. You can see this curve on the outside here, it's having to be pushed further. Whereas actually the bottom here is being pushed inwards, isn't it? It's being pushed slightly inwards, okay? So if you see that, great, fantastic. If you didn't get it, make sure you add it on. And if you still don't quite understand it, make sure you grab me and we'll go through it in the lesson. Okay, let's move on. And let's think about our second new term that we introduced today, the idea of stress. So let's have a think about stress. So let's define stress to start with. So stress is simply known as force divided by area. So what I'd like you to do first is pause the video. As per usual, can you come up with the units for stress for me, please? Stress is known as force over area, but what's the units? Okay, hopefully you've recognised that force measured in newtons, area is measured in meters squared, so the units are going to be newtons per meter squared. Now that's remarkably similar to a quantity, a unit that we use for another key physical quantity. So I'd like to pause the video. Can you just write down what you think that other key physical quantity that we often use in physics is measured in newtons per meter squared? Pause the video. Can you write that down? Have a think and see if you can write that down for me. Okay, so hopefully you recognise that this newtons per meter squared is exactly the same as if we were talking about pressure, which kind of makes sense really, because if you think about it, pressure is nothing more than force divided by the area over which that force is exerted. So this kind of definition kind of makes sense for both of them, and they're both very similar properties, both very similar quantities, but of course we talk about them in completely different contexts. Okay, stress we talk about in terms of a material and a certain property a material has. Pressure we talk about more generally in physics, atmospheric pressure, pressure of a gas, all those kind of things. So they are subtly different in terms of their context, but actually in terms of how we might think about them, how we might work them out, they're very, very similar. Okay, now what I want to think about is how we can start to relate stress and strain together. And in the same way that for a small force, when a small force is applied, force divided by extension will give us a constant. The way that stress and strain relate together, okay, the ratio of stress and strain will give us a constant as well. Okay, now this constant is known as Young's modulus. So, given that information that the ratio of stress to strain okay, gives a constant, and that constant is known as Young's modulus. Can you write just a quick formula for Young's modulus? Pause the video and have a go at that. Okay, so I said to think about stress and strain being as a ratio giving us a constant, okay, and that constant we call Young's modulus. So Young's modulus, okay, which we actually give the letter E to. Don't ask me why, but that is given the letter E, okay, as a symbol. So if you sometimes see that written down, you might see it written down as simply E, and we say that Young's modulus is equal to tensile stress divided by tensile strain. So hopefully you got something like that down. If you didn't, what I'd like you to do is in a second pause the video and add that in. But before you do that, there's another thing I'd also like you to have a think about. We know that strain is extension over length, and we know that stress is force divided by area. So can you input that information, substitute that information into these two quantities, and come up with a simplification for this formula so that we can do the calculation in one stage rather than having to do it in two stages. So pause the video, have a go at that. Make sure you've got this definition down, and then can you substitute in the definitions for stress and the definitions for strain. Have a go at that. Okay, so I've asked you to do a quick substitution in for stress and strain to give us Young's modulus. So hopefully what you've said is that Young's modulus E, okay, is equal to force divided by area, okay, and then we can divide that by the strain, which is given to us by extension over length, okay, and then hopefully you've recognised that if we say force divided by area multiplied by, and then if we flip this strain quantity, we can say that it's multiplied by length over extension, which then becomes force multiplied by length divided by area times extension, and that gives us Young's modulus. Okay, hopefully that's what you had already. If you haven't quite got that down yourself yet, okay, pause the video, take a moment to copy it down, and make sure you fully understand where that quantity, or how that derivation, how we've arrived at that final formula, which is FL divided by AX is equal to Young's modulus E. Pause the video, make sure you've got that. Okay, and if you've got that, what I'd like you to do is just have a quick think about what the units for Young's modulus are as well. Okay, have a think about that. Pause the video and see if you can write down what the units for Young's modulus are. Okay, so hopefully you've recognised that it's just newtons per metre squared, because our strain is unitless. It's our dimensionless quantity, as we said at the beginning, so therefore it's not going to have any impact on the units for Young's modulus. The only thing we're taking into account is will be the stress. So it's just newtons per metre squared again. So I'll just quickly add that on. So make sure you write that down onto your sheet as well, that the units for Young's modulus are newtons per metre squared. And then the last thing I want you to think about, okay, on your sheets, can you write down a method for how we can calculate stress, strain, and or Young's modulus? Okay, because these are quantities that we're really interested in. It's what engineers are really interested in when they're designing new structures. They're not particularly interested in the force extension graph, but they are interested in quantities like stress and strain and the Young's modulus of the materials which they're using. So that's much more useful in terms of real-world application, and that's what I'd like you to think about. How can we measure Young's modulus? How can we measure stress? And how can we measure strain? So what I'd like you to do is, on your sheets, there's space for you to write a method for calculating those three quantities. Okay, so if you'd like to write a quick method, you might like to draw a diagram as well, and make sure you bring that with you to the lesson. That's all for this flip, okay, that's the last thing I'd like you to do. Okay, so again, make sure you bring your sheets with you, just as all the other lessons, make sure you bring the sheets with you, and don't forget to respond to the video on Edmodo. Cool, thank you very much, and I'll see you in lesson.